Hi, I'm Jeff Yager. I'm a professor of chemistry, biochemistry, and physics at Arizona State University. In this screencast, we're going to quickly go over error analysis review, that is primarily used in laboratory, chemical and biochemical laboratories. Specifically, this one has been tailored for physical chemistry laboratory, where there's a lot of emphasis placed on data analysis and error analysis associated with this laboratory. And it's often the first time where students move beyond some of the simple kind of error analysis associated with significant figures and things like this, and move on to propagation of error, graphs that explicitly have error bars associated with them, and explicit calculations of those errors, not just random confidence level or percentages associated with the numbers. And so the first thing I think that always needs to be stated is oftentimes when students think error analysis, they think oops, mistake type analysis. They write a paragraph on, oh, well, maybe I didn't pipette this properly, or maybe a little spilled or something like that. When we talk about error analysis, that is not what we're talking about here. We're not talking about mistakes, or we're talking about random errors that occur, can be determined what they are, and propagate through measurements. And so, and that's what we want reported. If you literally made a mistake, then the experiment should be redone, right? You shouldn't be reporting things where you literally made mistakes. But you're gonna, all the experiments you report have an associated error with any number, with any numerical value in the lab. There is an inherent associated error in what that is. And it can either explicitly be stated or implicitly, and that's what we're going to more explicitly look at in this course. And so I give some very basic examples of what would you call this measurement, and with certain delineating properties for, in this case, volume. What you would be able to say the volume is plus or minus, a specific amount, based on how accurately you can really look at that and between two ticks tell where you are in this system. And so that's a very classic one. The other one would be, where you basically have a measurement and you can kind of estimate the plus or minus. And this is something I put right in the beginning because of how important it is. Error analysis, or a very statistical way of determining the error, usually involves multiple measurements. You can only do statistics on things where you have more than one of them. So if I told you to classically determine the weight of something and its associated error, what you would do is reweigh it numerous times and then do some type of standard deviation, etc. But you can also get a sense for this by estimating the error, and that's what this next section goes through. So while, of course, you could, for example, on a thermocouple, make a measurement, and then remeasure it, and then remeasure it, and see how much variability you get, and then look at the standard deviation and variance in that over several measurements, etc., to do a real statistical analysis. Oftentimes we practically make this measurement once, but you can tell just by how it's fluctuating, in that it's rarely a one-off measurement. You get something, and this is commonly seen when you do weights, when you do temperature, etc. And you can have a fairly good estimate of what your error is by not only the significant figures that is given to you on the thing, but also the inherent variability over time that you often see in some of these measurements. So you can estimate the error, and that's often practically done quite a lot. Then we move on to talk about how we report these errors or uncertainties in value. So that comes back to significant figures and what it should look like in certain systems so that you're being consistent with both what the error is and what you're showing as implicit in the significant figures you're showing from a number. We show, the classic way of looking at, with multiple measurements, the mean and standard deviation of a system, and then how you would use those once calculated to ultimately give you, what the error is and reporting it properly and in kind of a common format for showing error. And then, if you have measurements that are way outside of what look to be a regime, what you can do to test whether that data can be statistically rejected and not included based on real analysis. And then finally, and probably most importantly, that's for each individual measurement. But in physical chemistry, you're often doing measurements and then you're doing multiple steps of either data analysis or using multiple measurements to feed into equations and theories that often are multiple steps of processing equations. And you need to know how to propagate the error through that so that not only you learn the algebra to propagate the numbers themselves, but we need to learn how to propagate the error associated with each of the numbers as well. And so I go through an example of a very simple one to begin, just how the density is related to the mass over volume. So again, we know how to do the division of the mass over volume, etc. But almost, I won't say non-intuitively, the error doesn't follow the same algebraic. This error, because of its random nature, is done through looking at partial derivatives with respect to each variable that has associated error in it. And then taking, because you don't care if it's randomly fluctuating up or down, that's why you end up taking the square, square root of the square of the number. Of each of those components. And then we give an example with this density equation and give a few further examples as well. And this is shown quite a lot. And then we move on to showing a least squared fitting, typically done in plotting programs, which again, it often has been seen before. And as you can see, now we start looking at explaining how a least squared works and what you would do to start putting error bars on some of these. And finally, there are numerous resources. So this is just meant to be a handout I made as an overview. So hopefully this handout and a quick explanation of this helps. And this is definitely a major component to each of the laboratory projects you do in Chem 343 and other both on-ground and online physical chemistry and advanced chemical laboratories. Thank you.